Thank you very much. I hope you can all hear me fine. Yeah, I like the title. Maybe I should have changed it to Breaking into the Black Box. Sounds a bit more exciting than explaining complex machine learning models. But yeah, that's exactly what I will be talking about. I will tell you a little bit what these models are, why we call them black boxes, and basically I want to convince some of you, at least some of you, that it's something that is interesting and maybe worthwhile considering, incorporating into your own workflow. So before I start, the obligatory about me slide. So I'm a biologist by training. I did the whole shebang with lab work and PhD and 2 years of postdoc where I did lots of bioinformatics work analyzing next generation sequencing data. And it was clear for me that I didn't want to stay in academia, so I got very interested in machine learning and wrote blog topics about this kind of thing and incorporated machine learning into the biology data I was working with at the time. And so somehow I ended up as a data scientist in a company where I've been working for 1.5 years almost. So just before I start, to give you a rough idea what you will hopefully learn in the next 45 minutes, or let's say 30 to 45 minutes. First, I will introduce machine learning models as black boxes, why we call them black boxes, and why I want to argue that it makes sense for us to try and understand them a little bit better than we do right now. I will also talk a bit about ethics and morality and all these topics that have been somehow touched by the two keynote speakers yesterday and today. So what is interpretability to do with fairness and bias and transparency and all these things that are important when we think about implementing models that affect humans in their personal lives. And I will get a little bit into this much discussed topic of, is there now a right to explanation with the new data regulation? And finally, I will show you a few methods how we can actually achieve explanations or approximations to explanations. One of them is LIME. I will explain how LIME works, and I'll show you how it can be applied to text data, to image data, and to just regular tabular models that we build with machine learning algorithms. And I will also show you some alternatives and the newest paper that follows LIME, which is called Anchored. So the first section, I'm not sure why this is, maybe it's better like this. So the first section, interpretability of machine learning models. So I want to start with this very provocative statement that lack of understanding leads to mistrust. So when we think about AI, of course, you are all very versed in the topic, I guess, so you probably all generally trust your models, or at least you are not afraid of AI as maybe some of the people who are not as used to these topics are, like the general public. Your grandmother maybe, she might be a bit scared even because she doesn't know what all these models and things actually do, if they are dangerous or if they are not. And that's also a bit because we don't really understand them. And when we think about machine learning, and if we want to implement this in society and have AI become like really a part that helps us in our daily lives, we want to think about how different groups of people might be thinking about machine learning and AI and what they basically want to do and expect from these models. So on one hand, there is the data scientist or people who work with data who maybe train these models. I'm guessing a lot of us are data scientists. I myself am a data scientist, so we are very deep into the nitty-gritty of training models, getting data, cleaning data. We are very much about achieving high accuracy or low errors and reducing our loss functions. And we look at all these numbers and get really excited often by, yay, look at my model. It has a very low error rate, and I reduced my loss to such and such numbers. Isn't it great? But we also often are in the position that we need to sell our models. So when I'm with a customer, for example, and I build my models and I'm super proud of my model, it's not enough that I know what I did and that I trust my model, but I also need to communicate to the customer that this model is doing what it's supposed to do and what it is doing, and that it's actually solving the problem that it is supposed to solve. Because on the other hand, we have the user, and the user might be someone who is affected by the machine learning model, who maybe uses it in terms of if I want to get a loan from my bank, and my bank applies machine learning models to determine whether I'm creditable for a loan or not, I might want to know if maybe I don't get the loan, and maybe I want to understand why it is. Or some other cases, we can imagine if machine learning becomes more prevalent in medical diagnostics and it makes a certain diagnosis, I want to understand, of course, why a certain decision has been made by a model, and I want to understand if it's reasonable to me. And the third part here, I wrote a little bit separate from the others, is the politics, not as a real person, but like politics in general. All the politicians want to protect, of course, or their task is to protect us from harm and misuse, and there, of course, the topic of transparency becomes very important. So why do I even talk about interpretability? Because AI and machine learning, as you all know, are not super new. Neural networks have been around since the 1940s, 50s, so it's not something that's just like since yesterday. So still, interpretability is a topic that has been more and more in the scientific literature in the last years. And I think a few of these reasons are, of course, AI and machine learning become more omnipresent, and in particular in our everyday lives, of course. You all know your smartphone, and you write emails, and you get email suggestions from Google, you have spam filters, you encounter AI or machine learning models in everyday life without even thinking about it. And because these models are so efficient and often so much faster than humans, they will become more omnipresent. On the other hand, society is becoming more and more aware of data safety, and data privacy, security is becoming a really big topic that's not at least discussed by the EU lately, and it's talked about in the media. How dangerous is it that our data is collected by Google and Facebook, and where is it stored, and what's happening with the data, and can our insurer maybe get this data and do something, whatever they want to do with it, but maybe there is some potential for harm there. So it has become an increasingly political topic as well. And of course, we can say it's a bit hyped when we read articles by the media. They are often not clearly presenting rational evidence. They are often like either it's amazing, it can do everything, it will save the world, or it's like, be aware, we will have robots that kill us when we are not careful, right? So it's very important that it's not just this mystical, magical thing that's doing something, but that we have really means to understand these models better and to explain them better. Because, of course, AI is complex, right? Otherwise, it wouldn't be able to do all these amazing things that it can do because it is so complex. But this complexity, of course, inherently makes it difficult to explain to lay people what is really going on behind the closed door. All right, so why are we even discussing this? Why do we say machine learning models are black boxes? And that's basically because we observe this trade-off between interpretability and complexity. So when we think of very simple models with a low complexity, we usually it's very easy to understand what's happening. Like if we have a linear model, we can very easily understand the linear relationship that's behind this model, right? But if we have more complex models, so here you can see just a few examples of linear relationships. But if we have more complex models like neural networks, for example, they are much more complicated in how they work and in how they determine, how they learn, basically. So they are able to learn very complex tasks, but this comes with a trade-off that we are not able to really understand what's going on anymore. So the big question you probably noticed behind all this is, can we trust our models? Like, can we safely put them out, deploy them, and have them make decisions that maybe affect people's lives? So this question of trust right now is often answered by pure performance metrics. So when I look at a typical machine learning flow, it looks something like this. We usually have a step where we collect data, we prepare our data, we clean it, maybe we transform and normalize, whatever we want to do with it to make it ready for our machine learning models. So then we go ahead, we train our models, we maybe compare different algorithms, whatever, and in the end we choose a model that we say is the best. And what's the best? That usually depends on the problem, but it generally is measured with some kind of performance metric, be it accuracy or loss or mean squared error or what have you. And that's usually where people stop right now. So we accept that our model is good based on some criteria that we define, but we don't really trust our model in terms that we don't really know what is going on. So why does the model make the predictions that it makes is still the big question, right? So and I want to argue that we should improve our understanding of models for three reasons. And the first one is that we can improve our models if we understand them better. So if we know why the model makes decisions that it makes, I know if it makes sense to me on a human level. So it's not always the case, of course, but very often if you have image classification models or if you have something where you need a certain expertise in the field, you can have some sort of sanity check if you understand which features contributed to a decision and can judge whether that makes sense or it doesn't. So maybe it can be used then to prevent wrong conclusions in the beginning or maybe even to understand and prevent adversarial attacks. So here are three examples from the paper of Lime. I'm not going to go into details, just three examples where you can use image classification tasks and understand your model better and detect biases that maybe the model didn't actually learn to differentiate between wolves and huskies, which is the first example. But even though the performance measurements were perfectly fine on the test set, it turned out what the model actually learned was not the wolf or the husky, it learned the background because the training set was biased in the sense that most of the wolf images had snowy background and the other ones didn't. So what it learned was the background and not the actual object that we want to detect. So here, that's a very simple example where you can just very easily see if I had known this before or if I could have tested why my model made these predictions, I would have seen, okay, this does not make sense to me on a human intuitive level, so maybe I should go back and retrain my model. Can do similar things with text data, knowing which words in a text classification model contribute to decisions or predictions can help you determine whether it makes sense or not. So trust and transparency is, of course, the second big group why we should invest time and energy in understanding our models, because I need to know what is the model's decision based on in order to be able to have a transparent message to the public who is affected by this model. So, of course, if we think about very extreme examples like machine learning models applied in medicine, it can be, of course, a question of life and death. If I have a model that's supposed to detect brain cancer and it maybe makes a prediction for one patient that this isn't brain cancer, but it was wrong, of course, that would be a really bad thing, right? So if we know why a model makes these predictions, the doctor can then very easily take these models and determine whether they are trustworthy or not. But even in business where it's not life or death, nobody will probably die if your model doesn't detect a fraud case right away. But still, if we know before we deploy a model and before we test it for maybe months and months or weeks that it didn't learn the right things, maybe we can save some money and time and improve our models before we actually deploy them. So what goes, of course, hand in hand with trust and transparency is to prevent bias and to create models that are fair. And we can think about many cases where this comes into play when we think about morality and society and ethics. So here are a few examples. I already talked about the credit loan credit check cases where we have models that predict whether a person can get a loan or not. And of course, if there is a societal bias in the data that we train these models on, let's say that colored people were historically less likely to get a loan because the societal bias was the reason for it, and all the complicated things that go along with it, this will of course be in the data, and what the machine learning model will learn is probably going to reinforce this bias. And if we don't know why the model makes its decisions, if it's just a black box, we can say, all right, it works. Maybe the bank has super good numbers because it's not losing any more money because it doesn't give loans to people who can't pay them back. Nobody will talk about this, but if we know that our model makes this decision on features that might be societally biased, we can talk about this much more easily. Similar example is the parole example that Joanna mentioned yesterday in her keynote, where the California state law system has this model, or they experimented with this model that helps judges make the decision if a prisoner is likely to become, how do you say it? To be in jail later again in his or her life. So the model will suggest if a prisoner is eligible for a role or not. And of course, you can imagine the same thing, particularly in the US. There's much more colored people in the judicial system just because the society is biased. And this is something that will, of course, be reflected in machine learning models if we train them on this data. Similar thing that might be also a case in Germany, it probably is if we have job candidate matching. So if I as a woman apply for a machine learning job, maybe the model learned that there have only been 5% women in the past, and it's not as likely that a woman is the correct fit for this model just because of my gender. This would of course be obviously very biased. But if we have no way to check our models and to check what feature actually gave the strongest impact on the decision, we have no real way to check for biases and to address them. So the next thing has probably been discussed to death, and you have all answered all these emails that you agree to the new data regulations, but also for us as machine learning engineers, or whatever we call ourselves, there are these articles 13 to 15 and 22 that have this very interesting passage in it. And the main part, actually, the controller shall provide, of course, the following information, whether there is the existence of an automated decision-making, so whether there is an algorithm that makes a decision, and the more important part has to provide meaningful information about the logic involved, and so on. So I'm not a lawyer or anything, so I don't know if this is really something that means we have to give an explanation if somebody asks us, but it might be. So definitely it will not be as easy anymore to just say, I don't understand my model, it's a black box, so what can I do? So now you know why I think that it might be interesting to find these explanations. But how can we actually do this? And there are several methods, because what we don't want is to go back to our simple models, where we have the ability to understand them, but we still want to have our complex models that can do all these amazing things and that are so much more accurate, but we still want to have at least some sort of explanation. So, and what I mean when I talk about interpretability and explanation, it's more than feature importance. You probably all, if you have worked with machine learning models, you have determined feature importance, but that's not exactly what is meant by interpretability of the decision a model makes. So these are a few of the more popular approaches to at least get approximations of what the model does. So one of them is called the breakdown package. We have tree surrogate models, we have Shapley values, we have a partial dependence, ice plots and ale plots, and the two newest methods are called Lime and anchors. And these are actually the two I will explain in more detail today. I mean, the other ones are interesting as well, especially Shapley values. If you are interested in game theory, I suggest look into Shapley values. But here, I'm going to skip this because it's a bit late already and go right away to Lime. So LIME is one of these approaches that will give us approximations of explanations for the decisions that are made by our models. So it's called LIME. It stands for Local Interpretable Model Agnostic Explanations. And it's exactly what it says, basically. So it's model agnostic. This means that it can basically be applied to any classifier. And it will find local explanations. And it's been written in Python. You can read more about it in this paper by Marco Ribeiro and colleagues. There's also an adaptation for R, and all the analyses I will show you have been done in R, but in Python it's very similar. It's just 2 lines of code, basically. So LIME works with 3 basic principles, and the first one is that explanations are given one instance at a time. So it will not give you a global explanation of how the model works. So what I mean with global is that it will not give you all-encompassing rules that will be true for every instance that you test with your model. It will only look at instances separately and look at what are the features that contributed to the prediction that is made on this one instance. The second principle is that a simple model will be fit locally to predictions. And locally just means, again, we will have our one instance and we will fit locally and see how can we explain the prediction with this instance. And another very important principle is that the explanations will be given on the original features. So even if we have, let's say, a complicated neural network that will have, let's say, 3 or 5 layers or even more layers of abstraction of our data, and the prediction finally, of course, will be made on all this complicated calculation with all these abstractions of your data, LIME will go back to the original input. If we have, let's say, tabular data, we have our input features, and it will go back to these input features to have explanations that you can interpret as a human. So this video you can watch later. I will provide the slides, of course, and it will give a nice overview of LIME. But this is the basic workflow of LIME. So you have your original machine learning model. Let's say I trained a neural network or a random forest or gradient boosting model or whatever. I will take this complicated black box model, and I will now want to have an explanation for one instance or sample. So I will take this instance, or LIME will take this instance, and what it will do first, it will perturb or permute this instance. So it will replicate this one instance and change it a little bit each time. So we now end up with a collection of very similar data points where only small changes compared to the original instance are there for each one. So we will now take this collection of perturbed samples and use our complex model, our black box model, to run it against all these different data points, basically, and make predictions. So this is the first part that we have, the predictions on the permuted data set. Then we will also calculate the distances between these perturbed data sets and the original instance. So we will know how strong was the difference, basically, or what we achieved by changing something between the original input and the perturbed sample. So then there's something called determining the most important variables. I'm not going to detail how this works right now. You can read it in the paper or in the package manuals. But just to know that it will not make prediction or explanations for all the features that you have as input. Let's say you have 500 input features. That's way too many to make sense of as humans. So the suggestion is to have, let's say, between 5 or 10, maybe a bit more features for which you want to have the explanations. So now we take these distances and similarities and use them as weights in our local model. And our local model can be any simple interpretable model, for example, a linear model or a logistic regression model or something like that. So in this way, we will get approximated explanations for the features. And how this looks like, I will show you. So I will skip the details here. So this is how it would look like if we have a tabular data models. So here I trained a data set, I think, from UC Irvine about chronic kidney disease, where the response variable is whether a patient had chronic kidney disease caused CKD or not. And each instance is a patient, and I trained my model on it. I think it was a gradient boosting model, if I'm not wrong. You can read the code, so I will always provide the link to the entire code, how I made these models on the bottom there for you to check out later. But basically, I trained this machine learning model, and now I use Lime to get these explanations. And if it's a tabular model with like tabular data and input features, this is how the output will look like. So you will have these are the first 3 test cases that I had. So case 4, case 7, case 23 are just different IDs of the patients. And you will get for each patient the explanation. And you have on the rows there, you have the feature. You probably can read it, and the value that the feature had. And if it's a green weight, a very big weight, this means that this feature supported the prediction most strongly in this case. Red features are those that contradict the prediction. We can also use Lime for image classification models. And here I used a Kaggle data set of fruits, and I trained again an image classifier. I trained it with Keras and TensorFlow. So what we can do then is take Lime again, use our Keras model, and basically do the same thing. The only really big difference is that here Lime will work with superpixels, and superpixels are these areas of very similar pixels that you can see here for 2 example images of a banana and a clementine. And what Lime will do is basically go through all these things, just that with superpixel it will randomly turn off certain superpixels and see how the prediction changes, and we'll get either a heat map, or you can have these grayed out values that show you only the superpixels that support the prediction. In our first case, if you can read it, it's predicted to be a banana with a probability of 1, and here you see only the superpixels that support this prediction, and the image below has been correctly classified as a clementine. Also here you see that, for me, of course, for us humans, it's very easy to interpret these results and see, okay, our model did really learn features that make sense to us and not just maybe a background. And the last part, Lime can also be used with text models, and here I trained a text classification model with XGBoost on women's clothing reviews, also a data set from Kaggle, and used Lime to get the explanation. Here, the first review, absolutely wonderful, silky and sexy and comfortable, is predicted to be a 1, and 1 in this case means that it's a 5-star review. And it's 97% sure that this is a 5-star review, and the words that support this prediction are wonderful and comfortable. The words that contradict this are absolutely and silky. And what you notice here, there's also always an explainer fit in Lime that tells you how good the local fit is. And this is important because, of course, Lime is not perfect, right? There are some pitfalls and problems that you will always have with Lime. And one of these is always this explanation fit. So here in the first case, it's 94. This is pretty high. But I very often have cases where the explanation fit is very, very low. So basically not trustworthy at all. So, and the reason is, of course, that we only use these linearly weighted combinations of our input features, and the coverage is not clear. And there has since been something called anchors by the same people who developed Lime, and they proposed this new method to get explanations that is better, or that at least addresses some of these problems that Lime has by using if-then rules that apply locally to predictions. And what they will do is they take an instance again, similar to Lime, they perturb it again, similar to Lime. So what you will then get is basically rules for each of these prediction, basically. So if my feature has this and this value, or if it's in this and this category, and then it will test this rule and test it, basically how often does it hold true. And it will only call a rule an anchor if it's true in a certain proportion of cases. So you can change the value which you want. You usually have a high probability, let's say 95%, you call them anchors. So there's also the link to the paper and to the Python implementation of the package, where they will give, of course, much more detail how this works. And if you want to know more about anchors, I will talk about the paper at the This Week in Machine Learning and AI Europe meetup. It's an online meetup. Can go to the site and check it. It will be beginning of November, I think, and there we will discuss this paper in more detail if you want to understand how it works. But the output will look very similar to LIME. You have on the right an explanation for text classification models that will give you now rules for which words were associated with a certain prediction and which were not. So now you have, for example, here, this case, not bad is an anchor for a positive classification, and not good is an anchor for a negative classification. And the same thing, again, it can be applied to tabular data, to image data, and to text data. So here, the basic difference between the image classification explanations of LIME and anchors is that in LIME, the superpixels were randomly turned off. With anchors, the superpixels are randomly replaced with just a random image. So here, that's why these pictures look so weird. So here you can now see examples for a bit complicated anchor rules. So you can have more than one feature. You have combinations of different features that make up these sets of rules that you can use to explain your models. So the take-home message, I hope that I could convince you that it's an interesting thing to think about and that it makes sense to maybe consider adding this extra step to your machine learning workflow to try and understand your model a little bit better. Because I want to argue that we as data scientists are the people who probably understand our models the best. We really know what's going on. We worked with the data. We know the data really well. We know the models really well. So I also want to encourage us that we take responsibility for the decisions that our models make. So I want to make sure that my model really does what it is supposed to do, that it learned the right features, and that I can trust it and that I can give it to the public and be reasonably confident that it will not cause any harm. And particularly with things like LIME and anchors and all these other methods that are developed and that are being developed, it's so super easy. It's just basically 2 lines more of code that it's really not an excuse anymore to say, I just can't explain my models, it's a black box. You can at least try. Yeah, and with this I want to thank you very much for your attention, and I'm happy to discuss and answer questions.